Welcome to electrical machine 1 course, and we are discussing about the armature reaction and its ill effects on the performance of a DC machine. And that too I am not using primarily any mathematical things, with physical reasoning trying to understand that. And we have seen that these are the poles, this is the armature, and there are brushes here in the quadrature axis, which is otherwise a magnetic neutral zone. There is no B in this direction when the machine is under no load condition. This I assume north, this I assume south, and so on. And then I told each coil has to cross from this side to that side. A little while ago, if a coil was here carrying cross and dot current, after some time the same coil will come here and has to carry dot and cross current. Therefore, current changes from plus I to minus I. And mind you that there will appear a quadrature axis flux along this direction M A because of so many conductors. I will slightly digress because I cannot resist but say another interesting thing. I told you that these are the things dot, these are cross, and this coil is now undergoing commutation. Direction of rotation I assumed like this, generator mode, that is the thing. Now, see, while studying induction motor, all of us know that suppose it is a slip ring induction machine. Slip ring induction machine, how do I access the rotor terminals? Rotor terminals of a slip ring induction motors are accessed by slip ring and brush arrangement. Slip ring is a continuous ring and brush is touching, is not? Slip rings are continuous rings, 3 slip rings will be there, and there will be fixed brushes, which I am showing like this, 3 slip rings and 3 brushes. These are continuous rings. And why it was necessary? Because I want to access the rotor terminals. It is going to R phase of the rotor, this ring is connected to Y phase of the rotor winding, B phase of the rotor winding. So that these rotor terminals R, Y, B become stationary here, and you can connect external resistance this that in case of slip ring machine. In case of DC machine also, because the armature conductor is moving, how to access the armature terminals? We have not accessed it through slip ring and brush, because if you access it by slip ring and brush, you will get AC voltage. It was necessary that commutator segment and brush arrangement intelligently connected will convert a DC voltage. So, in case of a DC machine, I access the rotor terminals through brass and commutator segments. What is the fundamental difference between these two connections? Here, each terminal from this is brass in this machine, it is always connected to a particular coil end. As the coils move, etc., it never it is always connected to that coil, fixed coil, one side of a fixed coil. Similarly, this fellow is connected to one side of a fixed coil. But in this case, this brass through commutator segment is getting connected to different coils. When a coil comes to a particular position, then only this brass gets connected to that. It is not connected to a fixed coil end, otherwise you would have got AC like this fellow. So, that is why the rotor terminals in a DC machine is accessed by commutator segment and brushes to make it DC, and also when a particular coil come in this position, then only these two ends gets connected to brass, and different coils at different times comes. That is why this space, in space what is the position of the coil, whoever comes to that particular position in space, that gets connected through brass, that is known, okay, that is there. Now, another interesting thing I will tell. We have now learned what is the ill effects of armature reaction, generator mode. Now, suppose I want to say large machine, armature reaction will be quite heavy, is not. Armature flux, this MA depends upon IA straight away. If it is a large machine, large current, MA will be large, this quadrature B will be large, there will be large voltage, circulating current, and induced voltage in the coil undergoing commutation too will be large because of inductance effect, more flashover is expected. So, in a large induction machine, you cannot just have only field winding and armature winding and feel happy. No, it is not going to happen. There will be very large flashover. What is to be done then? See, without doing any maths and this that, I want to nullify the effect of armature MMF. Suppose I say that here is a conductor which carries cross current and it produces field around it like this, we have seen, fine. Now, suppose I say do something so that there will be no field because of this current. What is the answer to this? You will say that I will then place this was the original conductor, and in the close proximity I will place another conductor carrying same current in the opposite direction, and there will be no field external. Field will be 0, this fellow will produce this fellow will produce in the opposite direction. Net field in this will be, at least will become substantially small, field is 0 to the external world. If you have placed two conductors side by side in close proximity, not short circuiting each other, then this field will not be there, no field, approximately no field better to say. Therefore, if I want to, I know armature current will be carried the moment you load the machine, conductors will carry armature current, MA will be produced. Is it possible to place some additional conductors in close proximity of these armature conductors, which will carry opposite currents and of roughly same strength say. But where to put the additional conductors? Here is a place to prove those additional conductors. See, this is air gap G. Air gap length is very small, few millimeters, things like that, is not. And here is a space on the pole face. That is what I will do, what I am trying to tell. On the pole face, I will cut slots and put conductors like this. On the other side also I will do like that. Oh, sorry. On the other side also I will do like this, that is this one. I will put conductors like this. Conductors, this is stator structure, mind you, and this is suppose one turn, this is another turn, these are all stator coils. So, what can be done perhaps is common sense tells, I am not giving any mathematical calculation, that okay, on the pole face, this is called pole face. On the face of the pole, you have slots grouped in and place conductors like this, turns like this. And these coils are called compensating coil. So, what is the situation now in the DC machine? There were field coils, it was carrying IF. There were armature coils carrying current armature, current IA. In the conductors, of course, that is IA by A, parallel paths. And there is now another coil, which I will pass to nullify this MMF, currents in this direction. This is cross, and this side dot. Learning from this example, cross dot nearby U place. So, it was producing, armature was producing flux like this, compensating coil will produce flux in the opposite direction and they will nullify. And they will nullify, they will be in a position to nullify provided this compensating winding is connected in series with the armature. When armature current is 0, this compensating coil will not carry any current, it is not needed. When armature current is growing up, you are loading the machine up to rated current, then this current also this current increases. So, that for all currents you can compensate the armature winding. Therefore, I should now use like this to draw a machine winding, represent a DC machine, large DC machine. For small machines this is not done, because cost will be much more for such machines, additional windings. So, what you do, there is it is shown like this symbolically, field winding, this is F1, F2. Here is your armature coil A1, A2. And the compensating coil, magnetic axis of that is also along the quadrature axis, because these are the turns, cross dot. Are you getting me? Cross, coil comes here, another turns, and this runs on the stator structure, through that you make this winding. Therefore, compensating coil can be shown like this. Its magnetic axis is along the quadrature axis, and so while connecting, so this is compensating coil. Where it is physically present? On the pole face. It is present here. and say C1, C2 like that. And then you say that a large DC machine, large capacity DC machine, you connect this in series with the armature, this, and then connect the load. This is what you do. Got the idea? Therefore, it is always ensured that this is IA. The compensating coil winding current is proportional to IA, armature current is always proportional to IA. So, you choose suitable number of turns of this one, so as to nullify the effect of armature MMF. We will talk about selecting the number of turns later, but the point is, this is the thing. The idea is very simple, that is what I am telling, not really calculating how much should be the number of turns of the compensating winding. Another practical thing is, you should be very careful when compensating coil is there, you have to connect correctly. What I mean to say, that I could also connect the compensating coil like this, this is the armature for the same machine. Somebody, this is C1, somebody connects like this and C2 he takes, and this is the field coils. The what I want to mean is this: compensating coil is to be connected with appropriate terminals in relation to A1, A2. Suppose for the same machine, I connect in both the ways separately, I will do testing. In one of the case, it will compensate. That is, armature C1, suppose in this position, generator mode, this is MA, MC must be in this direction. Suppose in this position, when current leaves C1, it produces MC. Then only MC can balance MA off and reduce your armature MMF along quadrature axis, hence voltage induced in the quadrature axis in the coil undergoing commutation. But if it is true, then in this case, this is C2, sorry. In this case, what is going to happen? If this is the direction of IA, if this is the direction of IA, through C1 current enters, therefore, it will produce MMF also in the downward direction, and MA was also in the downward direction, situation will be worst. Therefore, while connecting compensating coil, you must properly connect, so that the MMF produced by compensating coil opposes the MMF produced by the armature coil, and then you get some relief so far as the commutation problem is concerned. Do I get really 100% relief? The answer is may not be, because see, the pole phase only extends not up to this zone, the pole is there from this to this. While calculating pole pitch, this is one pole, then there is another pole here, I drew it, flux per pole calculation, this is the magnetic neutral axis. So, in this zone, however, armature conductors are there, that is, it is up to this point, but after that also cross dot is there. Can it fully compensate this? No. Most of the armature MMF will get nullified in this process, no doubt. But if you want to get perhaps there will be some still quadrature flux which will be reduced, no doubt, but may be present. So, in that case what is done is that you this is the armature coil, this is the armature conductor, here is your field coil F1, F2, and here is your compensating coil. Okay. This can be compensating coil, I will draw later. What is done is this, let me draw here also the poles, so that you then get the idea of the term. So, this was the main poles, these are called main poles, north south, created by field coils, field coils. This is the quadrature axis. Now, what you do is this, in this interpolar zone, that is along the q axis, you produce some small poles, thinner poles, very small width. And that is your stator will look like this one. This is the yoke. And these are called interpoles. Thin interpoles, not this much large, only small this thing. And these are what? Field coils. These are what? Field coils. And these are what? You put another coils here. So, this is called interpole coils. For large DC machine you will find interpole coil. So, armature, if it is generator mode, generator rotating in this direction, we know these currents will be cross, this side current will be dot, only drawing two representative conductors, and your armature flux should be, when armature carries current, armature flux should, armature MMF will be like this. So, what should be the polarity of the current? So that this flux I will not tolerate. What should be the polarity of the current? To oppose this quadrature axis flux, if interpoles were not there, there would have been a flux that causes the problem. Therefore, I must pass cross current here and dot current there, not. Similarly, cross current here, dot current there. Like that I have to put, because there will be some quadrature axis flux present. And then, and this will take care of these nearby conductors. So, this fellow cannot compensate for all the armature MMF. Majority of the armature MMF, I will also connect compensating coil, whose axis will be same as the interpolar axis. This is the compensating coil, sorry. This is the compensating coil. I am just telling about the ideas. Perhaps there was problem when you have compensating coil, okay, you get rid of the armature reaction problem for majority of the armature conductors, but still you cannot compensate for conductors lying in this zone, because this fellow ends there. So, to avoid this flux till whatever is left, you connect some interpoles in this zone, and this machine therefore may be having, can be shown, one large machine may be having C1 C2 compensating coil, and also its axis is also along quadrature axis, and these are interpole terminals. By which name should I call it? Compensating, and this is interpole IP1 and IP2. And this fellow also is to be connected in series with the armature, so that it can react to any armature value of the current properly. So, that this then will become your armature terminals. I mean effectively to the load, then this will be the thing. So, to summarize what I am trying to tell, that qualitatively we have first seen what is armature reaction, and what are the ill effects of armature reaction, and then how to avoid the ill effects of armature reactions by connecting a compensating coil. Compensating coil will be pole phase coil, and also by, if you have enough money, then go for a almost fully compensated DC machine, having both compensating coil and also thin poles, thin interpoles poles, to nullify the effect of armature reaction. That is what I am to tell. Under no load condition, IA is 0, this fellow is not there, no poles. One should not be under the impression that okay, but at no load condition there will be induced voltage across the brushes, correct, but because of this field also there should be induced voltage, but that field is not there, is not, IA is 0. That is why you have made it dependent on the load current, so that it can compensate for all the currents. Of course, I have not told how to calculate the number of turns of interpoles, compensating coil, etc. If possible, I will tell you, but the physical reasoning are very important. Then only you go for computation. Okay, what are the things happening in a DC machine? If you want to connect it such a big machine as a generator, then treat these two as your armature terminals and connect field winding like that. I think you have got the idea. There are compound machines. I am not, mind you, I am not yet told about machines which has both field coils and series coil. That is different thing altogether. These two coils are to be connected in order to avoid the armature reaction effect. That is what we have discussed today, and in our following lectures I will in fact sketch this armature MMF in space, how it looks like, field flux in space, superimpose them, and same thing whatever I have got here will be also obtained there. Okay. Only last point I want to tell, that if you see this is not, this polarity has to be south, is not, this polarity has to be north, interpole polarity, cross dot lines of force will enter. You see the conductors, which is this point is very interesting. If you connect like that, how it will improve commutation? This coil concentrated on this coil, it was here on the left hand side, it was having cross dot voltage, is not, and you know after some time, after a brief period of time, it will cross this what is called this border line, go to the other side, and he is asked to carry the opposite current. This cross current is to be changed to dot immediately after it crosses. Now, when it comes here in this zone, there will be induced voltage because of the armature reaction north pole that we have studied, and also because of the south pole. I can choose the strength of the south pole so as to nullify that armature north pole here, opposite poles I have brought in, and induced voltage will be 0. The direction of the field was like this earlier under no load condition because of MA in this direction. What I have done? I have put another coil so that there will be a field there, these two may nullify, and therefore, quadrature B does not exist, no induced voltage, etc. And then it cross current, here the current will 0, then negative, okay, some sort of smooth changeover takes place. Now, I may make this compensating poles by selecting it number of turns a little higher than what is required to nullify this quadrature axis flux itself. That is okay, instead of north pole here, there when this conductor comes here, it will see a south pole. That means, this conductor was carrying cross current, it has to carry cross, no, nothing doing, because these are in series here. Then it reaches here, it carries cross current, but I have already started educating the conductors that look here, you are going to face a sudden south pole. So, I will rather start training him that you start experiencing a south pole from now onwards, so that it will improve commutation. It will be accelerated commutation. It will be very helpful to the conductor. It has to suddenly see a south pole, you start in advance that okay. That is, in this case interpole is designed not only compensate this B, but also overcompensate it, slightly overcompensate. So, that the same polarity which this conductor is going to face after a little bit of time start facing a little ahead. So, these are the nice physical reasonings with which one can go to understand what is going to happen in a DC machine when armature carries current. Thank you. We will continue with this in the next class.